So my talk today's title is the list version of the Borodin-Kostochka Conjecture for graphs with a large maximum degree. This is joint work with Professor Kierstead and one of his students, Landon, and they're both at Arizona State University. And the last author is Professor Reid, who's at McGill. So today this is the outline of the talk today. I'll start with some preliminaries and some history, and then I'll go through the outline of the proof and just some basic main ideas. And then I'll try to convince you that the idea actually works by obtaining a proper color, which you'll see what I mean later. So let's start with some preliminaries. So this is a graph. It's just a vertex set and an edge set. The key concepts today will be the relationship, well, not the relationship, but the clique number and the maximum degree. So the clique number of a graph is the size of the maximum clique of your graph. So the clique number of this graph here is 4 because you can see there's a complete graph on 4 vertices. And the maximum degree of this graph is 5 because this vertex here in the middle has degree 5 and every other vertex has lower degree. So let's get into coloring. So a proper K coloring is a function where you assign each vertex some color from between 1 to K, and when you look at every edge, the endpoints of that edge must be different. I mean, the colors of the endpoints of that edge must be different. And the minimum such K is called the chromatic number. So if you look at this graph, this is just K24. At every vertex, you have 2 colors available, which are red and blue. And this will be a proper coloring, right? Because if you look at every edge is incident to 1 red vertex and 1 blue vertex. So a natural generalization is called the list chromatic number, which I'll introduce this way. So a list assignment assigns to each vertex some list of colors that might be used on that vertex. So here in this graph, every list is the same. Every vertex has the 2 same colors available, namely red and blue. And in L coloring, right, given some list assignment L, and L coloring is a proper vertex coloring where you're assigning the color such that the color comes from its list. And the list chromatic number, which I'll denote by chi subscript L, is the minimum such K such that you can have an L coloring for any L assignment if you give each vertex at least K colors. So since this is a generalization, one would expect that the list chromatic number is at least the chromatic number because you can always vary the lists on the vertices. So if you give me the same graph, what I will do is I will give each vertex 2 colors, but I'll give some variation in the sense that not all the vertices have the same colors. Right? And I claim you can't find an L coloring given these lists, right? Because if I color this one with red, this one here, then since red is in both of these vertices, you're forcing yourself to use green here and orange here, and in this vertex you can't find a color. Or in the list of this vertex you can't find a color that you can apply. So this will be the theme of today's talk, right? If you give me something that's true about the chromatic number, I want to say, well, can it be extended to the list chromatic number? And this is one example that the list chromatic number and the chromatic number can be different. And not only that, it's known that it can be arbitrarily large. So let's look at some bounds on the chromatic number depending on the clique number and the maximum degree. So if you look at the graph and if you see a clique with k vertices, every pair must receive a different color. So every vertex must have a different color, which means the clique number is a lower bound on the chromatic number. And a very simple greedy algorithm shows that the chromatic number is bounded above by the maximum degree plus 1. Right? And another theme of this talk would be greedy is good. Right? Everything simple is better in life. So let me demonstrate this algorithm. So how does the algorithm work? You have some graph and you give some arbitrary labeling. And let's say you're trying to color this vertex here, given the graph beforehand is already colored. Right? And when you're trying to color this graph or this vertex, you have at most delta colors forbidden because you've already used those colors in the previous graph. Right? Therefore, if you always have delta plus 1 colors available, you can successfully color each and every vertex until the very end. Right? So this gives a very basic fact that the chromatic number is bounded by the clique number and the maximum degree plus 1. And it's a very famous question in graph coloring that where does chi stand, right? What's the chromatic number depending on the clique number and the maximum degree? So there's a very famous conjecture by Professor Reids who states that if you give me some graph, then the chromatic number must be bounded above by chi must be bounded above by omega plus delta plus 1 over 2. And the reason you have this ceiling here is there exists some graph where if you don't have the ceiling, then this formula over here becomes strictly less than the chromatic number. So this is just one famous conjecture. So back to this fact. Now if you remember the argument I used, the same argument can be applied to prove that this fact, right? Not only the chromatic number is bounded below by the clique number and above by the maximum degree plus 1, you can also bound the list chromatic number by the clique number and the maximum degree plus 1. Right? Because every clique still needs k clique still needs k different colors, and when you're applying the greedy algorithm, it doesn't matter what the lists are at each vertex, you're always forbidding at most delta colors. So if you have delta plus 1 colors available on each vertex, no matter what the colors are, you always have one available color, so you can finish the greed coloring. So the question here is, that seems, it's a sufficient condition, but is that always the case? Right. So there's another classical result by Brooks that states that, well, maybe not every graph, but a graph with sufficiently large degree, if the maximum degree is at least 3, then if you don't contain a clique of this size, right, if the clique number is at most delta, then you don't need delta plus 1 colors. You can always color it with delta colors. And this is from 1941. And somewhere around the 70s, the list chromatic number was invented. So Wiesing in 1976 proved the same identical result, but this time he proved it for the list chromatic number. So another question here is, can this be extended? So this is a result from Brooks and Wiesing. So Borodin and Kostochka in 1977, 1 year after Wiesing proved this result, asked, well, if you forbid the maximum clique you can have, right? If you forbid a clique of size delta plus 1, and in addition, if you forbid one more clique, if you forbid clique of size delta, then do you actually need all of these delta colors here? So they gave a conjecture that, well, if you give me some graph, again, delta has to be sufficiently large. If you give me some graph with sufficiently large delta, then when you forbid these two big cliques, can you reduce the number of colors available? Can you reduce the number of colors required? And the number here is sharp because there exists a counterexample when delta is 8. So I'll talk about some history. And this conjecture here is the same thing as this one, it's just a different phrasing, right? If you give me a graph with sufficiently large degree, you take the contrapositive and if you say, well, if chi is strictly bigger than delta minus 1, then omega must be strictly bigger than delta minus 1, which means it contains a clique of size delta. So let's start with this conjecture. So in 1977, Borodin and Kostochka made this conjecture, and 3 years later, Kostochka proved that, well, you don't have a clique of this size, but you have a clique of delta minus some constant, where that constant is somewhat big, namely delta minus 28. And the thing you see here is that there's no condition on delta being sufficiently large. So 3 years after that, Mosen proved that, well, if you give some slight condition that delta has to be at least this small constant big, then you can guarantee a clique of almost size delta, but there exists still this constant. So there seems to be some trade-off between having a condition that delta needs to be sufficiently large and guaranteeing a clique of big size.
But the Kostochka theorem, the degree isn't sufficiently large, it doesn't say anything, right?
Yes, it's some degenerate result. Yeah. So it seems to be delta here must be at least 29,
right,
or 30. Right? Yeah. So yeah, I had these two results to emphasize what's going to come. In 99, what Bruce Reed proved is if you give me some huge, sufficiently large delta, then I can finally guarantee a clique of size delta. And if you read his paper, he demonstrates the algebra such that it's nice. So he has this result 10 to the 14th. And there's this last section in the end where he claims it's still true if you reduce this down from 10 to the 14th to 10 to the 3. But he is skeptical about, well, maybe it's not true for delta at least 100. So there seems...
The proof does not work, or he thinks the theorem is not true.
He thinks using his own methods, you can't do any calculations on the constants better and better such that you will get 10 to the 2. So this is Reed's theorem. So what we prove is, well, as I was saying, the theme of this talk is we're trying to extend results from the chromatic number to the less chromatic number. So we prove, well, if you give me some sufficiently large graph, if you give me a graph with sufficiently large maximum degree, then I can guarantee you this clique, which is actually saying this, right? If you forbid a complete graph with delta plus 1 vertices and delta vertices, then I can bound the list chromatic number using delta minus 1. Right. So this is what I'll try to prove today, or at least show a sketch of this proof. But there might be some question that you guys are asking here, right? So Wiesing in 76 proved that, well, if you forbid one clique, if you forbid the clique on size delta plus 1, then the list chromatic number is at most delta. And what we prove is if you forbid two cliques, the clique on size delta plus 1 and delta, then I can get rid of one color, and I can just say, well, all you need is delta minus 1 colors. So the natural question is, well, can we do more? Right? And if you notice, this statement here is not in a box, and the reason it's not in a box is that it's not even true for the ordinary chromatic number when k equals 2. So this is just some nice closure that says, well, you don't need to do more than delta minus 1. Are there any questions? Right. So this is all the history.
Can you go back?
Yes? Yeah. So if you prove this for the list chromatic number, it's naturally true for the chromatic number as well. Because the list chromatic number is a strengthening of the chromatic number. But what I'm saying here is this is not even true for the ordinary chromatic number and when k equals 2. Right? You can imagine this is delta minus 0, this is delta minus 1. So what happens if we try for delta minus 2? But it turns out there's a very easy counterexample.
What is the counterexample?
I believe the counterexample is you have a big clique and you join it with a 5 cycle. I think, yeah. Any more questions? Okay. So let me try to show you how we proved it. So this is the main theorem. And as any mathematician would do, you just grab a counterexample, and then you give it a list assignment, right? After all, we want to prove that if you give me a graph, then I can demonstrate how to get some coloring from the lists. Right? So this graph G will be a counterexample from now on. And the clique number of this graph will be delta minus 1. And even though I claim it's a counterexample, I will show you how to get this coloring that we want. But we first need an observation that G has minimum degree delta minus 1. Now this is a very simple observation, but this fact will be used over and over, or this technique will be used over and over. Right? So why does G have minimum degree delta minus 1? Because let's assume G has some vertex here that has degree at most delta minus 2. Then we will remove that from the graph, right? And then we will apply induction. And how many colors can appear in its neighborhood? You can have at most delta minus 2 because we assume that the degree is delta minus 2. And we will try to color this vertex back. And we always have a color available in its list because the list size is delta minus 1, and we only forbid delta minus 2 colors. So that proves this simple observation. But using this, we will actually prove more. And it will come in the slide after the next one.
So I have a question. So
yes?
you are applying induction hypothesis when
yes.
you delete the vertex. But what happens if you delete it and the maximum degree decreases?
So
you have the delta condition. Delta is bigger than.
Yes. Well, yeah. So it's not really simple as this, but it's you get the idea, right? So here's an outline, or how the proof works, right? First, we will decompose G into smaller parts. And the reason we want to decompose G into smaller parts is so we can apply the local lemma, right? What the local lemma says is whenever you're doing a probabilistic argument, you want to say, well, when I'm applying a sequence of events, I don't care how the events happen if they're all independent. If they're all independent, I can just say, well, I'm applying the same experiment over and over again and give me some bound. But what the local lemma says is, well, you can actually allow some dependency among the events, right? You're saying I'm going to conduct some experiments, and even though not all of them are independent, if sufficiently many of them are independent, I can still guarantee the existence of the structure or the coloring you want. Right? So I'll come back to this later. So once we decompose G into these nice smaller parts, what we're going to do is we're going to actually randomly color this graph. Right? We're going to apply the naive coloring procedure, which I'll define later. Right? So we're going to color this graph randomly so we get a good enough partial coloring, right? When we're doing this coloring, we always want to say, well, we have a proper coloring, and then we're going to improve this proper coloring until we can color the entire graph. And the way we do it is we use Asuma's inequality. Right? So Asuma's inequality is a concentration type result that says, well, if you have some expectation, if you have x as a random variable, then the probability that x deviates away from its expectation is very small. Right? So we're going to try to force some structure or some safe vertices, which I'll also define later. So we're going to try to say, well, the number of safe vertices, the expected number is very high, and then what we say is, well, since the expectation is high, the probability it deviates from its mean is going to be very low. And if the probability is very low, we can apply the local lemma and say, well, since the probability that you don't have these bad things is very low, we can say, well, none of them actually happens. So once we guarantee the existence of this good partial coloring, we're just going to color greedily and finish off the coloring. So this slide is actually the same slide that will be at the very end of the talk. So we'll see if I did a good job explaining.
So in the Asuma's inequality, you have T1 up to Ti, and there you have T1 up to Ti minus 1 and Ti prime?
Yes. So if I understood correctly, everything before this comma here and here is the same. So Asuma inequality basically says when you have this random variable, I'm just going to change the outcome of one event. It doesn't have to be the last experiment. I'm just going to change the outcome of some experiment that I conducted in the middle and see how much the random variable x varies. And now I'm going to sum up all of them at the very end and use that to bound the probability that our random variable deviates from the expectation. Right. So this is the outline. Excuse me. So let's go back to graph theory. So this is a naive coloring procedure. This is how we will try to randomly color the graph. Right? And it's very simple. You're trying to randomly color the graph, so all you do is for each vertex, you have a list of available colors. So you just randomly choose any color you want from that list with uniform probability or uniform distribution. Right? But of course, if you just randomly color it, some parts of the graph will have conflicts, right? Bits and parts of the graph will induce monochromatic subgraphs, and it won't be a proper coloring you want. So what's the most simple thing to do? Just delete it. So what you're left is still a proper coloring, but it doesn't cover the entire graph. So it's a good partial coloring. So here's an example. So here's a graph, and I will just randomly color the graph from its I will just randomly choose a color from its lists. And let's say I get this coloring. Okay. Now if you look at the red subgraph, you have a path on 3 vertices, which is not good, right? Because of this, it's not a proper coloring. So what you do is you say, well, I don't want that to happen, so I'll just delete it and leave those vertices uncolored. But if you look at the graph, you still have a monochromatic blue subgraph. So you do the same thing. You say, well, this blue edge is not good, so I'll just delete both colors. And you're left with this vertex. So this seems very naive, but this also does something very good, because let's say if this vertex here, if green was included in its list, and if this color black, I don't know if you can see it, if this black color was not in this list, then this vertex is very happy. Why is this vertex happy? Because you look at this vertex, it has maximum degree delta. So maybe delta colors appear here, but you don't care about this black one, right? Because this black one is not forbidding a color from its list. So you have at most delta minus 1 colors appearing, but that's not even true because you have a repeated color. So at most delta minus 2 colors are appearing in the neighborhood of this vertex, which means whatever happens on the neighborhood, there's always going to be a color available in its list to apply to this vertex. Does that make sense? So this will be the main idea, and this is what I mean by a safe vertex.
Once you remove all of them, when you say you pass on length 3, like then you let leave one color.
I mean, we could, but then since we're trying to apply these random results, we want to say, well, if some repeat happens, we're just going to delete all of them. So we're doing this stupidly here so we can have a nicer analysis at the end. I spent half of the time coming up with the argument and half of the time doing calculus, calculating all these deltas. Thank you. Any other questions? So this is, So after applying this naive coloring procedure, you have a safe vertex here, right? This vertex is safe, and that's what this definition is. Right? So a vertex, which is uncolored, right? So an uncolored vertex is safe if one of these happens. Right? And basically what these conditions do is these conditions guarantee that whatever happens in the neighborhood of that vertex, there will always be a color available in its list that we can apply to that vertex. Right? So for one example here, this is the first case. If a color repeats 3 times, right, we can do the same counting argument. Right? If this vertex has degree delta, then how many colors may appear in the neighborhood? Well, delta, because it has delta neighbors, but one color is repeated twice. So you only have delta minus 2 colors, delta minus 2 different colors appearing in the neighborhood, which means since this vertex has list delta minus 1, you still have one color available in its list that we can apply. So that's the concept of this safe vertex. And everything else is the same, it's just different cases because this black vertex is not in the list, which is good because it's never going to forbid a color from your list. And one thing to note here is that if you have a vertex that's uncolored, and if 2 of its neighbors are uncolored, then you can apply a color to that vertex. Right? Because since 2 of your neighbors are not colored, you have at most delta minus 2 neighbors. Since 2 neighbors are not colored, you have at most delta minus 2 colors appearing in your neighborhood, which means you still have a color in your list available. So now let's try to obtain this proper coloring. Let's see. So what are bad when you're trying to color a graph? The things that are bad when you're trying to color a graph are these cliques. Right? The complete graphs are very bad because they're very dense and they restrict each other. So what we try to do is we analyze these cliques. And we come up with this nice argument that says, well, if you give me a clique, well, a big clique, and when I say big, it has size at least 3/4 delta. Then what it's going to do is it looks like this. You have this clique, and maybe I have to remove this one vertex. But as you saw, we're dealing with delta at least 10 to the 20, so we don't really care about this one vertex. So let's ignore that one vertex. So we have this clique, and we remove maybe one vertex. Then we can partition the clique such that each part has the same list. Now I won't give a proof of this, but this is the concept of a core, right? So each part has the same list, but not only that, this core, right, this set of colors appear in every single vertex of this clique, maybe except one. Right. So, and this will be very.
What does this partitions? Can you say again?
So if you.
There's a bunch of vertices in each part, and each vertex has the same list.
So there's a bunch of. You give me a clique, and I can partition the clique into smaller pieces, such that each piece has the same list. So every vertex in this part. Every vertex here has the same list, every vertex here has the same list, every vertex here has the same list. But not only that, this core, right, a certain set of colors appear in every vertex of this clique, except maybe one. So after...
So this is not a probabilistic.
This is not probabilistic. This is just simple trying to apply induction where you take away... where you apply induction on G minus this clique.
Oh, so
and
this
then
is a property on minimal counting.
This is the property of G, right? We're always talking about this minimal counter example now. Yeah. So this existence of a core is very nice, because as we saw when we're trying to force these safe colors, if a color is repeated in its neighborhood, that's very good. But after we know that we can partition this clique into these smaller parts, where this core appears very frequently, we know that the probability that you have a repeated color in your neighborhood is going to be very, very high. But I'll get to that later. So this is the core. And not only you have a core, if you look at a vertex that has many, many neighbors inside this clique, then we can say, well, this core has size delta minus 2. Which is basically saying, if you give me a clique with maximum size. Right? After all, the bad things are the maximum cliques. So if you give me a maximum clique, and if you look at a vertex that has very high degree within the clique, then we know every neighbor of that vertex has a core and some special color. And this color only appears among the vertices in here. So we prove these lemmas, which says, well, each color, each special color, only appears in 5 lists, which means each part has size at most 5. And we also prove that this vertex doesn't appear all that often. So this is just some lemma, which is not really part of the probabilistic method. So we decomposed these cliques, and we saw the structure of how it looks. So now so the natural next step is to decompose the entire graph. So if a vertex is sparse, that's somewhat good, because if it's sparse, then maybe it's not in a clique or a big clique, right? Because after all, these big cliques are bad. So what we do is, there's this lemma by Professor Reid that says every graph has a very nice decomposition, where the decomposition looks like this. You give me a graph, and I can say, well, there's this one set that has all the sparse vertices. Well, I shouldn't, what I said was wrong. I can decompose the graph such that there's one set that has sparse vertices, and every other part is either a clique or a clique with one vertex. And this clique is a big clique. And what I mean by big is it has size delta minus little o of delta. So it has size approximately delta, but maybe smaller. So this is a very nice decomposition. And after we have this decomposition, what we can do is we can apply the local lemma. Right? So we have this decomposition. So we want to, after we have this decomposition, we want to partition these cliques even further so we can make our lives easier when we're trying to apply the local lemma. So the most important clique is a clique where you have some vertex. So this is a clique, and this script P sub 3 is the set of all cliques where there's some vertex outside of the clique that has many, many neighbors inside C. So after we partition this, what we want to do is we want to say each sparse vertex is safe, and each clique has 2 safe vertices. Right? So how do we force that? The way we force it is we use the local lemma. We say, well, you have this part S, that's a set of sparse vertices. So we'll say, well, let S sub V be the bad event that V is not safe. And also we want to force 2 safe vertices in each clique. So we say, well, let's let this event be the event that this clique does not contain 2 safe vertices. So if we assume this doesn't happen, then I'll demonstrate how to finish the coloring. And after I demonstrate how to finish the coloring, I'll show you one case of how we force this. So let's see some series of nice pictures, right? So let's assume none of these bad events happen. So that's what this means, right? The green means that vertex is safe. So you know, So what we'll do is when we're applying the naive coloring procedure, we'll only apply the naive coloring procedure to this part. To the sparse vertices, the vertices that are contained in S, and the vertices in P script 1, 2. Remember, these are the clique. Each clique here doesn't have a high degree vertex outside the clique. So once we apply the naive coloring procedure, because we assume none of the bad events happen, we know each vertex in S is safe, and each clique has 2 safe vertices. So now let's look at the remaining vertices in this part of the graph. Right? Each vertex here is in this clique. So that vertex is adjacent to 2 safe vertices. And if you remember what I said in the very beginning, if you're adjacent to 2 uncolored vertices, there always exists a color in your list that you can apply to yourself. Which means I can give a color to every single one of these vertices that are not the safe vertex. And the same thing to this one special vertex here. So I will give that one color to that vertex. So I will color everything in this area except the safe vertices. And now all I have left in this part are the safe vertices. And by the definition of a safe vertex, you can always color a safe vertex no matter what happens to its neighborhood. So I can finish the proper coloring on this part. So now we have a subgraph that's completely colored. So the question is, what happens on this part? And that's where this P sub 3 comes in. So P sub 3 doesn't say each clique has 2 safe vertices. It says it contains 2 vertices that can be used, that the special color on the vertex can be used on that vertex. So let's say you have this clique, you have this clique. So every clique in P sub 3, remember, had a high degree vertex outside itself. So that vertex might be here in some other clique, or it might be here in this graph, in the colored graph. So we will uncolor it. Right, that became gray. So let's consider a vertex here. If a vertex here, remember this is a clique, this is a very big clique. If it has one neighbor in this part, we can apply the special color of that vertex to this one. So that's good. Now the question is, what happens if this color is in this vertex? What happens if the neighbor of this vertex is out here in the colored graph? And the reason we defined P sub 3 like this is to say, well, even if this happens a lot, we can still find a bunch of these vertices where you can apply the special colors to these vertices. So after we found these vertices, we will give it the special color. And what does this mean? By the way I define the special color, a special color is unique to that vertex. Or at least what it means is all these other vertices that are adjacent to this one does not have the special color in its list. So we can find 2 safe vertices in each clique. And then we repeat the same process we did on this part. Because each vertex here, here, even this vertex and this vertex is adjacent to 2 safe uncolored vertices. So we can color everything else first. And then we can color the safe vertices, which gives us a proper coloring of the entire graph. So this is a very contrived way of coloring the graph. Right? The reason I had to split up the graph into these 2 parts is that in the very beginning, we tried to apply the naive coloring procedure to the entire graph. But when we did that, the bound that we have right now, which is delta at least 10 to the 20, could not be before I divided it up into 2 parts, we only had 10 to the 70. We only had 10 to the 70. And after we split the graph into these 2 parts and we apply the greedy process twice, we could finally lower it down to 10 to the 20. So that's why we have this complicating coloring procedure. So now in the remaining 10 minutes, I'll try to explain how to use the local lemma. So as I was saying in the very beginning, the local lemma says, well, now you know what we're trying to do. We're trying to color the graph randomly, right? We're trying to pick a color in each vertex's list independently at random every single time. And the bad events, as you saw, were these ones where this one is not safe, where some vertex is not safe, or some clique does not contain two safe vertices, or some clique does not contain two vertices that will force two safe vertices. So what does this mean? This means if you give me some clique, a clique is not independent from other cliques, right? Because this clique and maybe this clique have two adjacent vertices. And when we're trying to apply this random procedure, maybe we will remove a color from the other clique, which makes these two cliques dependent. So if you consider one clique, a clique is mutually dependent or not mutually independent to at most delta to the 5 other events. Maybe there should be a constant up here, but we really don't care about constants. So the reason it's delta to the 5 is that if I change the color of this vertex, the color of this vertex affects the color of this one and this one. Right? Because if this color is red, 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 that means, okay, maybe if this is red, blue, red, if I change this color from blue to red, I will have to remove the color of this red and this red at the same time. And that will affect the number of safe vertices in each clique. So if you go from here, it's delta, delta squared, delta cubed, delta to the 4, and the last delta kicks in because each clique has size about delta. So that's where you get delta to the 5. So now we showed that this d here is delta to the 5. So if we want to apply the local lemma, we have to say p is at most delta to the negative 6. Right? We want to say the probability that this bad event happens is very, very small, namely delta to the negative 6. So I won't go through all of these, but just one case, I think I go through this one. So let's just fix some clique that has this size. So remember, if you give me a clique, I can say, well, maybe except one vertex, this concept of the core exists, such that this core is in every single vertex. And what I'll do is, remember what we want to force is this concept of a safe vertex. So each of these vertices that are labeled C is safe. Why are they safe? They're safe because this C and this Z receive the same color, which means eventually they will be uncolored, because this is a clique and these two are adjacent. Also, this color light blue or sky blue is not in the list of C, which is good, and this color brown, I think, which is not in the list of this color, which is not in the list of this one, is also good, which means this vertex has two colors appearing not in its list in its neighborhood, which means at most delta minus 2 colors can appear, which makes this a safe vertex. And that's the same for each and every one of these. So both colors here don't appear in this list, so that's why this one is safe. This one, both colors here, this one color and this color, these two colors both appear in its list, but it doesn't matter because they're repeated. So if they're repeated, that's also a criterion for being safe. Right? So the way we'll guarantee that the probability of this bad event happening is very low is that we'll say, well, let's just be stupid and calculate the expected number of these safe vertices. Right? Let's say, well, if you apply this random coloring, then we have this many safe vertices by expectation. And then by using Asuma's inequality, I will say, well, the probability that the the probability that the random variable deviates from its expectation is very, very low, which means the probability that this bad event happened is very, very low. So in the end, all we have to do is show that the probability that x deviates from its mean is very, very low. So I'll go through this case. Or maybe first I'll calculate the number of safe vertices. So in order to calculate the expected number of safe vertices, I first have to calculate the number of these P3s, right? Because these P3s are the good structures that will force us even some slight possibility of having a safe vertex. So if you give me a clique, and of course I always have to remove this one annoying vertex, and you give me a P3, what I'll do is I'll just be greedy and grab a maximal or a maximum set of P3s. And I'll give this extra condition where each endpoint has at most 4 neighbors in this clique. And the reason I have this condition is so the calculation is nicer. So by a previous lemma, we know each vertex here has at most 4 neighbors in this clique. So it has at most 3 neighbors in this part, this C sub I minus A. And each vertex here can only have 2 vertices outside of these 2 boxes. Because if it has 3 vertices, then one of them might have more than 4 neighbors inside C, which is okay. But then we have 2 left, which means from that vertex we would have a P3. So this is just some basic counting that I'm going over very quickly. So after counting some edges, we see that we can guarantee some linear in delta number of these P3s. Which is very, very good because once we guarantee a linear number of these P3s, we know that the expectation of the number of safe vertices can be very high. Right? Because since delta, all the graphs we're dealing with has delta at least 10 to the 20, this means the number of P3s we have is at least 10 to the 15. So now we know we have at least this many P3s. So now let's try to apply the the naive coloring procedure and see how many safe vertices we get. So whenever you have a P3, what we'll do is we'll look at the 2 lists. And if the 2 lists have a very high intersection, namely if the intersection is at least 2/3 delta, then we know many of these overlap. But not only that, we know the list here and the list here overlaps as well. Why? Because of the very first lemma I showed you. Right? If you give me a clique, then there exists a core that appears very often in that clique. So since this vertex and this vertex has 2/3 delta many colors appearing in both lists, that means these two since these two have many colors in common, and since these two have many colors in common, that means these two vertices have many colors in common. Which means the chance that there's going to be some color repeated is going to be very, very high. And if these 2 vertices don't have many colors in common, that means there exists a lot of colors that are in the list of A, but not in the list of C. Which means the probability that this vertex is going to be safe gets higher and higher. So what we'll do is we'll just pick a vertex here in this clique, and we'll pick a vertex here in this clique again, and we'll just pick these 3 colors such that we get what we want. And then we just do some counting or some probabilistic analysis. We say we're going to let this be the event that this color alpha, which I think is red, is used on A, but not here, right? Note that it must not appear in its neighborhood because we want to keep that color. right? Because if that color disappears by the naive coloring procedure, then this vertex here won't be safe anymore. Since we want to make this vertex safe, that color must be retained on that vertex. So that's why here, when we say, well, we want to use beta on B and Y, it shouldn't appear on its neighborhood as well, because if it appears, but if it also appears on its neighbor, then we're going to delete it because of the naive coloring procedure. So after we calculate this, we get the probability that this event happens is at least this ugly number. And when delta is sufficiently large, we can simplify it and say, well, it's at least this nicer number. And then all we have to do is count the indices, the possible indices. And after we count the possible indices, we just multiply the two together. And it says, well, the probability of this instance happening is at least this small number, 0.003. But this isn't the worst case, right? Depending on the intersections of these P3s, this number varies, because both of them might have high intersections, both of them might have low intersections. Turns out the worst case is when both of them have high intersection. So the expected number of safe vertices becomes this. Because of not this probability, but some other probability, which I think is 0.00191 or something like that, multiplied by that number, becomes this number. So after that, all we do is we apply Asuma now. So we get that the expected number of safe vertices is this. And when we're trying to apply Asuma, we say, well, we're going to have these n trials, where n trials is just you're trying to flip a coin and say which of the colors in your list you want to apply to the vertex. So that's our trials T1 through Tn. And we say, if we want to change one color somewhere in your experiment, let's see how many safe vertices you might destroy. So if the color you're trying to change is one of these vertices in the P3 or one of these here, then the number of P3s you'll destroy is at most 2. Right? Because by changing this color from blue to orange, you destroy this one. But not only you destroy this one, you destroy this one as well. So, and the other case when the color you're trying to change is not here is a little bit easier, and it gives you a nicer bound. So after we know that, all we have to do is plug this in here. And since for sufficiently large delta, some delta to a number is at delta to -6 is at least this expression, the proof is done. So this is the same slide as the outline. So maybe you have a better understanding of what I was trying to do. So the first step is you grab a minimum counterexample, and then you decompose it nicely. So we try to apply this local lemma, because the local lemma says even though some bad events are dependent on each other, we can still bound the probability. And then we will color it randomly. We will apply this naive coloring procedure, and we will force a good enough partial coloring. And by good enough, I mean every safe vertex, every sparse vertex is safe, and every clique has 2 safe vertices. And then we will apply Asuma's inequality to say, well, the way we force these 2 safe vertices is by plugging 2 here. Right? Because all we need is at least 2 safe vertices. And for the remaining graph, we just color it greedily. So the moral of the story is, all we have to do is find a way to color the graph greedily, and then you get a nice result. Thank you.
Okay, thank you. Do you have a question?